If you write out a geometric equation, it is generally easy to find numbers that satisfy it, as long as you allow for continuous decimal values. But if you lock the rules so that the answers must be strict whole number fractions or integers, the math becomes incredibly difficult. The search for these precise whole number solutions dates back over 4,000 years. By 2000 BC, Babylonian mathematicians were carving vast lists of exact Pythagorean triples, like 3, 4, 5, into clay tablets. By 250 AD, the Greek mathematician Diophantus formalized this pursuit. He was completely uninterested in approximate decimal answers. He wanted exact geometric properties built exclusively from rational numbers. If you map all the possible real number solutions to a classic Diophantine equation, like the Pythagorean theorem, you get a continuous 3D cone. Every single point on that surface is a valid decimal answer. But if you filter that same surface for rational solutions, answers that are strictly whole numbers or clean fractions, most of the cone disappears. You are left with isolated points, specific coordinates scattered sparsely across the geometry. In 1637, Pierre de Fermat adjusted this base equation, increasing the exponent beyond 2. He claimed that for any higher power, the geometric surface was entirely empty of integer solutions. That claim, known as Fermat's last theorem, became an impenetrable blockade. The search for a proof stalled the brightest minds in mathematics for 358 years. Mathematicians couldn't solve this because our standard number line is built exclusively to measure continuous distances. To find these hidden rational points, they had to abandon the number line entirely and construct a geometric universe with an inverted definition of size. Let's start with a mathematical thought experiment. Take the number 5 and square it. You get 25. Square 25 and you get 625. Square that and you get 39,625. In every step, the answer perfectly matches the trailing digits of the number you started with. We can continue this process infinitely. By continually isolating the trailing digits and squaring them, you can construct a massive number that expands infinitely to the left of the decimal point, rather than the right. This creates a 10-adic number, written in base 10, with infinite digits. And because of how we built it, if you take this infinite string and multiply it by itself, it returns the exact same sequence. It is its own square. If a number equals its own square, we write that as n squared equals n. Move the terms to one side, factor them, and you get n times n minus 1 equals 0. This invokes the zero product property, a foundational rule of algebra. If two numbers multiply together to equal 0, at least one of those numbers must strictly be 0. Our infinite base 10 number is distinctly not 0, and it is not 1. Yet when you plug it into this algebraic equation, the math works out to 0. We have two non-zero numbers multiplying to make 0. The root cause of this error lies in our numbering system itself. Base 10 is composite. It's made of 5 times 2. Because of this, you can multiply two entirely non-zero numbers, like 5 and 4, and still generate a 0 in the units place. Constructing infinite numbers in a composite base shatters the laws of algebra, generating false zeros. That means base 10 is permanently broken as a tool for advanced number theory. In the late 1800s, the mathematician Kurt Hensel found a structural fix for these zero divisors. He realized the solution was to restrict these infinite expansions to prime number bases, creating systems called p-adics. To see why primes solve the problem, look at modular arithmetic. This is a system where numbers cap out and reset back to 0 once they hit a specific value, called the modulus. It operates exactly like the hours on a clock. On a base 10 clock, you can jump forward in increments of 2. After 5 leaps, you land perfectly on 0. You have multiplied 2 factors to hit the modulus exactly, generating a false 0. But if you construct a clock using a prime number, like base 3, the mechanics lock. Because 3 has no smaller internal factors, it is mathematically impossible to land perfectly on 0 in non-zero increments. By isolating the math to prime bases, the strict laws of algebra are restored. It becomes safe to build valid infinite number expansions without breaking the equation structures. Once the algebra was secured, mathematicians set out to graph these infinite prime numbers. The result is a geometric topology utterly divorced from the standard number line. Let's build the foundational layer of a 3-adic number system. We begin with the units digit. In base 3, that digit can only be 0, 1, or 2, which gives us 3 starting pathways. The next digit in our infinite string corresponds to the next power of 3. From each of our 3 base choices, 3 new, narrower possibilities branch upward. Every time we calculate a higher power of 3, the branches multiply. We aren't expanding outward, we are zooming further inward, creating an infinitely dense, disconnected fractal structure. P-adic numbers do not plot left to right on a flat timeline. They form a continuous, triply branching space, where calculating higher mathematical exponents maps to smaller physical spaces. This physically inverts how we view numbers. Multiplying by higher powers of your prime base shrinks the geometric footprint of the number on the graph. Because of this inversion, the concept of distance operates differently here. In a p-adic universe, 2 numbers are considered close together, based strictly on how long their branches match before they finally disagree. The exact numerical size of the distance between 2 points is determined solely by the first decimal place where their digits split apart. It is fair to ask why mathematicians are allowed to simply invent a bizarre new rule for determining size and distance out of thin air. They can do it because an absolute value, the mathematical definition of distance, only has to satisfy 3 abstract axioms. The first is the positive definite rule. Distance can never be negative, and it can only be 0 if the number itself is exactly 0. The second is the multiplicative rule. The absolute value of a product must equal the product of the absolute values. And the third is the triangle inequality. The distance of a sum cannot exceed the sum of the individual distances. The inverted p-adic metric perfectly satisfies all 3 strict axioms. Because it passes these tests, it is a mathematically legal geometry. Any theorem proved inside this branching fractal carries the full objective weight of reality. To see how this fractal geometry operates in practice, we bring back Diophantus. He posed a problem requiring 3 nested squares to sum exactly into a larger square. Finding a rational solution requires solving this infinite geometric series, 1 plus 3 plus 9 plus 27, and so on. The formula for an infinite geometric series is 1 over 1 minus r. Plugging in our ratio of 3 gives -1/2. Plotted on a standard real number line, ratios greater than 1 rocket to infinity. The numbers explode outward, entirely diverging. Using that convergence formula here is mathematically illegal. But we are no longer calculating on the real number line. We are inside the 3-adic topology, where the rules of convergence have shifted. In the 3-adic metric, higher powers of 3 are geometrically smaller. Because of that inversion, our ratio of 3 is actually less than 1 in absolute distance. Because the absolute value is strictly less than 1, the sequence doesn't explode. Instead, it spirals inward, legally and perfectly converging to a single coordinate inside the fractal tree. In this universe, the infinite growing string of base 3 integers precisely equals -1/2. By abandoning our standard intuition about linear size and calculating within the p-adic geometry, a purely divergent, exploding geometric series snaps into a pristine, exact rational value. Now we can take that 3-adic fraction, -1/2, and plug it straight back into Diophantus's ancient geometry equation as the variable x. Squaring -1/2 gives an area of 1/4. The next square is 1/16, and the third is 1 over 256. Add those areas up, and they perfectly equal 81 over 256, which is exactly a larger square with sides of 9/16. An abstract fractal geometry of infinite primes generated a flawless, rational solution for a physical square. This sieve is exactly what Andrew Wiles relied upon to slave Fermat's last theorem in 1995. Wiles mapped the mechanics of the theorem into these alternate numeric universes to hunt down the behavior of the integers. During his calculations, he famously executed the 3-5 trick. When his proof hit a mathematical dead end deep inside the 3-adic tree, he simply hopped universes into the 5-adic tree to bypass the blocker. Kazuyakato compares continuous real numbers to the sun and discrete p-adic numbers to the stars. The sun blocks out the stars during the day, and humans are asleep at night and don't see them, even though they are just as important. To solve an impenetrable problem in our reality, we must invent an entirely different universe, with completely different rules of size and distance, to finally see the solution.